Now let's denote every script by a circle. So that's the script for a fan. That's my localization. That's my mapping. That's my planning. That's my control. So that's simple enough. And the sensors, so this controls the actuators, and the sensors are, say, vision and a LiDAR only. Now it turns out that the scripts are not really independent. The scripts are parallel for sure, but the scripts are not independent, and the scripts actually cannot be independent in nature, because if the scripts are independent in nature, that means they will have independent inputs and outputs. Now, how do I localize? I localize with the help of input from my mapping server, with the help of inputs from my vision sensor, and with the help of inputs from my LiDAR sensor. How do I do planning? I do planning by getting my localization from the localization system, getting my goal from some human robot interaction, which is static. So that rarely changes. So that's how I do my planning. How do I do my control? I take the trajectory output and I calculate the error, and that error is what is given to the control, which is of the motors. How do I do my mapping? I always take my location as the input. Fan is easy, it's an independent script. It doesn't need any input from anybody. It doesn't give its output to anybody except for the dynamic server, of course, or the physics-based server, of course. So this sends image, this sends LiDAR readings. This sends a map, this sends the pose, this sends the pose, and the goal and the trajectory, roughly speaking. And this is a graph which shows how the different entities, they need to talk to each other, they need to exchange information. Now, here also, and of course, the image is also given to the mapping, and the LiDAR also is given to the mapping. We looked at things like artificial potential field. So currently deliberative and reactive planning both are there, and that also relied upon LiDAR readings. So you calculate the repulsive force based on the LiDAR reading inputs, because they are moving people that are not a part of the static map, they are part of a dynamic map. For that you need to read the LiDAR readings. Now that is something which is interesting. That's something which is interesting. Now imagine a physical LiDAR sensor. So that's a laser ray and it can turn around. Now that's a resource. The localization system blocks it. And takes its readings. The mapping system blocks it and takes its readings. And the reactive planning, which is the artificial potential field, blocks it and takes its reading. Now, you've got one sensor and it's a resource. So it's like a printer. Three entities cannot access the printer at the same time. So when one is printing, two are in the queue. When the other one is printing, two are again in the queue. When one is printing, then the other two are in the queue. So everybody is in the queue. And therefore, they actually share a lot of common resources and a common data. And because they share in common resources and the common data, the problem is if one module blocks the sensor, and remember that emergency stop was also a functionality, and that was using the LiDAR sensor, and this has to be extremely quick, otherwise a person will collide. And if I've got a piece of code that's directly accessing the LiDAR sensor like a potential field, it's doing a lot of calculations. Emergency stop cannot access the LiDAR. So it's an interesting programming problem where you've got physical resources which are blocked when one module reads it, or multiple modules are reading the same data for different purposes. A LiDAR reading is being read by emergency stop for emergency purposes, the mapping server for updating the map and calculating blockages, the planning server for calculating the repulsive forces of the potential field, the localization to calculate my position, and each one of them has a different frequency, or for different amount of time or for different periods of time it can actually block the physical sensor, and therefore I need to encourage resource sharing. Which means that one LiDAR reading will be taken by the physical sensor and shared with all needed modules. And that's easy. The LiDAR sensor takes the sensor readings, it stores it in a memory. Everybody has access to this memory. And this memory is read-only, so you can only read from this memory. So you don't need to put locks and blockages. When the LiDAR sensor is updating the sensor readings, it will put the temporary block, it will update that up, and everybody will access that from the same memory. So we've got in parallel scripts which are running, and there are two problems. Number one, the parallel scripts are sharing data. That means there has to be some mechanism of data sharing, either inter-process communication messages, or if they are physically different servers, then there needs to be a way to send data from one physical server to the other. Robots will have lots and lots of physical servers. The backbone of a self-driving car has many servers that run in parallel. So do our physical robots. There are many servers. One server does only vision, another one does only mapping. So there should be a way to share data across with it. And the second problem is that whenever you're dealing with physical resources, the data computed by one physical resource should be available for everybody as and when used. So that I don't take LiDAR sensor readings and then somebody comes and takes a new sense of readings, but then your reading and my reading are different because you read it at a different time, I read it at a different time. I cannot use your value, you cannot use my value. So there has to be some resource sharing also, which is possible. And therefore, we actually handle this thing, all this information interchange, all this communication, all this one node giving data to the other node, all this one LiDAR sensor takes its readings and shares it with everything by an event-driven paradigm. So there's an event-driven paradigm which is involved. So let's just take one node over here, which is vision, image, and localization. Now, what the localization system does is that it cannot access a physical camera first of all. It has an access to a common memory, a common resource that it has an access to. And now do you expect the localization system to again and again check if memory has been updated? Again, the problem is this will work at a different frequency and this will work at a different frequency. So let's say this works at 10 hertz and this scan potentially works at 1000 hertz or 100 hertz. So that means the localization system really needs to wait for the vision camera for updated information. And In computer program, this waiting is the localization system continuously checks the vision camera. Did a new information come? 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 And it keeps on checking this thing infinitely in a loop. And that's problematic. Now, some people might say that, it's waiting for 10, this was operating at 10 hertz, so let it wait for 0.1 seconds. But what if some information came and it waited an extra 0.08 seconds only because it did not know that the new information is there? That's also wrong. This 10 hertz will change. Sometimes it will increase, sometimes it will decrease, depending upon what other things the processors are doing. So we say that this itself is an event-driven paradigm where the localization system registers with an event manager as someone interested in the image data. So localization system says I'm interested in the image data, and vision camera also registers with event manager as a supplier of image data. So the vision camera, as soon as it refreshes the image, it lets the event manager knows, and the event manager just makes a call to the localization system. Hey, there's a new image. So you don't have, localization system is carefree. Whenever there is a new image, it will get a call from the event manager. So the localization system supplies one of its function that whenever there's an image, just call this function, and that's called as a callback function. And similarly, of course, is your eStop, is your artificial potential field. So the event manager, when the event manager gets a call from vision camera that yes, there's new data, it actually calls up all these and lets them know that there is a new data and they should just get, that's the excess of the data. So the callback function is invoked. So that's one of the way to handle communication. That's one of the way to handle information exchange. That's one of the way to handle resource sharing. Now I'll be using in some and my any programming script, which may be for localization, mapping, control, any programming script. It of course has an init section which is the first one called by the simulator to initialize the script. Thereafter you have the control part which runs into an infinite loop, and then you've got a destructor. So there's a constructor, there's a destructor, and there's a control step. There's an initialization part, there's a cleaning up part, and there's a control step, like any object-oriented program. So the simulator first calls the initialization script of every entity. So when you click on run, it first calls the initialization script of all the programs. That's where the initialization tasks are done, and then all the scripts run into an infinite loop. And finally, when the user presses terminate, end of program, ending, I don't need to continue the simulation, then the termination is called of all scripts, where all the cleaning up happens.